All right, so welcome back, and let's get going on today's class. So today we're going to finish up our look at Chapter 4, and then we're going to begin on Chapter 5, which is where we turn a corner in this course, start inferential statistics in earnest, and start doing some hypothesis testing. But before we do that, we still got to finish up with our look at some of those key ingredients that we need. And we need to finish up our look at the normal curve. So once again, we are so close to actually using statistics to answer questions about psychology, using statistics to take a look at data and figure out what's going on in that data. But before we get there, just a few more things to take care of. And as always, keep in mind where we're going, what is important about understanding and being able to do statistics. And one of the key ingredients, or one of the key goals that statistics allows us to accomplish is that it makes psychology accessible to everyone. So once again, the skills that we're developing right now is what's going to allow us to take 14 individuals, treat them with a new groundbreaking treatment. So once again, if you're in educational psychology, you might be dealing with autistic children. You might come up with a brilliant new treatment that you think is really going to help these autistic children reach their learning goals much faster. And if this new treatment actually works for these students, that is great. That is something that you can measure. That is something that you can know directly. You can directly see. Are they better after the treatment than they were before the treatment? You can actually measure those subjects. What you can't do without the skills we're developing right now is go any further. With just being able to measure how the sample did, you cannot intelligently generalize to a population. And I use the word intelligently because when generalizations to populations from samples are made on gut intuition, when they're made on just sort of a feeling that we have, or even when they're made with just us considering the things that we've seen, oftentimes generalizations from a sample to a population can be radically wrong. And one example of this is any form of racism or sexism, right? Anybody who has had dealings with individuals has had dealings with good individuals and bad individuals. Racism and sexism occurs when you incorrectly generalize from a small sample to an entire population. As psychologists, we can't fall for that. We need to be able to generalize intelligently, and when we develop that process, we can then help not just our sample of students, but we can help a population of autistic students. Any autistic student in any part of the world, we can let them know about this treatment, confident that this treatment will work for the population of individuals because we have generalized correctly from our sample to that population. So that's the skills that we're developing right now. And in order to do that, we got to go back and finish up our look at the normal curve. We got to go back and finish up our look at how to use this normal curve, this fact of nature, this distribution that occurs over and over and over again in the real world, because it is the distribution that occurs when multiple factors combine to form a single score. So again, if you recall, these ball bearings here fall into a normal curve because their position in this device is determined by how many times they hit a peg and go left and how many times they hit a peg and go right. And because that is done multiple times and those right and left moves add up to form their position, most of them end up in the center with a combination of lefts and rights. Very few end up all the way over to the edge with a combination of nothing but lefts or nothing but rights. And that again is something that we see especially in psychology, where a lot of our traits are made by multiple factors. All right, so today we're going to finish up our look at Z-scores. in a normal curve table, how to read the table, how to answer questions using the table. And then we're going to mention about an important idea of samples and populations. What's the relation between the two? The distribution of sample means, which is a very important concept, and we're going to end it up with the central limit theorem. All right, so hopefully you can remember, it was over a week ago because of the Memorial Day holiday, but last time we met in class, prior to the exam, we were taking a look at how to answer certain questions using the normal curve and then using the z-scores and the normal curve table. And we saw that when you're starting with a raw score, such as this question right here, if you have a distribution that has a mean of 500, standard deviation of 100, what percentile rank are you if you scored 333? You're starting with a raw score, a score of 333. You want to get to a percent. And we saw how we can follow those 5 steps right there to find out that if you did score 333 on your SATs, you're in the 4.75th percentile, meaning that over 95% of the population did better than you, meaning you need to take that SAT again. All right, so we did that one last time. Now we're going to do the flip side of this, which is where instead of starting with a raw score and going to a percent, you start with a percentage and you're asked for a raw score. You want to get a raw score from that percentage. So one question that will probably be on your minds and very relevant to you in the coming years is how do you get into the top certain percent for any distribution? So for example, you might be applying to grad school and they might need you to be in the top 20% of graduates, the top 10% of graduates. In this case, for this question, we are looking for what score do you need to be in the top 1%. So if you have a distribution that has a mean of 500 and it's got a standard deviation of 100 and you want to be in that top 1%, what score do you need in order to make it to that level? So this time, first thing to realize is that we're starting with a percentage. They've given us a percentage. They want us to recover a raw score. First thing we're going to do is we're going to draw the normal curve. Draw the area that you're interested in. Offload that from your brain so you don't have to take up your valuable working memory in order to try to remember that. So we draw our normal curve. Then we're going to make a rough estimate just so that we have a backup insurance plan in case we misread the table. Once we have the rough estimate, then we go to the table and we look up the z-score that's associated with that particular percentage. So in both of these problems, you always go through the z-score. You always end up going through the table, so make sure that you are doing that. Once we find our z-score, we check our answer against our rough estimate that we had in step 2. And then if everything checks out, we convert our z-score to that raw score using the z-score formula that we introduced last time. Actually, a few times ago. All right, so first things first, step 1, draw a normal curve. We are interested in getting into the top 1%. So we need to draw a normal curve that looks like the top 1%. And in our case, that's the curve right there. So the thing about drawing a normal curve that I want to reiterate, I got an Excel program that draws these things for me when I need to. But all you need to do is get the general shape of the curve, the general category of it. So even if you don't draw it to scale, as long as you draw a normal curve, draw the portion that you're interested in. We're interested in the top portion. That's 1%. What is that score right there? That's enough to offload your working memory so that you can think about the rest of the problem. So it doesn't have to be to scale. Just in general, you have your category, you have your visual aid. So that's what we're looking for. What score is going to get us into that top 1% of the distribution? So that tail right there, that's 1%. What score do we need to be in order to get into that tail? So we've drawn our normal curve. We're ready to go. We got 1% above, 99% below. Next thing we do is we want to make a rough estimate. So this rough estimate, you use the figure from your textbook. So let's bring that up right here. Let's bring that up right here. There we go. So we want to use this figure from the textbook. And again, remember that this figure here gives you sort of rough percentages. From 0 to 1 standard deviation out, that is 34% of the distribution. From 1 to 2 standard deviations out, that is 14% of the distribution. Ignore the plus 3, it's useless, I don't even know why it's in this curve. But from 2 all the way out to infinity, that's your final 2% of your distribution. So this entire side is 50, that entire side is 50, and this allows you to estimate the range that your answer should be in. So we want 1% above. So we need to approximately find where is 1% above in this curve. Well, this is 2%, starting at that line right there and going beyond. So we need less than that, right? We need an area that's less than that. So we don't know how much less, but we definitely know that it is less. So because we know that it's less, we can make our estimate that whatever number we find to be in 1% above, we need to have a number that is less than that particular area there. That's 2%, we only want 1%. So we're going to need a number, a z-score, that is greater than 2. Because a z-score of 2 gives you 2% in the tail. We want less than that, so we need a number that's bigger than 2. So that's our rough estimate. When we finally find our answer, it should be a number that is bigger than 2. If it's not, we did something wrong. All right, so we made our rough estimate. Next thing we do, now that we've prepared ourselves, we go to the table. We look up the z-score that's associated with that percentage on the normal curve. So this time we're given a percentage, so we don't look for a z-score and then read off the percentage. We look for a percentage and then read off the z-score. So keep that in mind whether you're looking up a z-score or a percentage. This time we're looking up a percentage. We need to find the correct percent. We need to make sure we're in the correct column. So the first thing we do is we look at our picture. Our picture, we have our percentage in the tail. This column does not look like the normal distribution we drew. This column does look like the normal distribution we drew. So we look our percentage in the tail in this column here. Occasionally when you're doing this, you're not going to be able to find your exact percent. So we want a percent of 1. We got a percent of 1.02 right there. We got a percent of 0.99% right there. So unfortunately, if you can't find it, you need to use the one that's closest. 0.99 is closest to 1%. It's just 0.01 off. So that is the percentage that we're looking for. Then we're ready to take a look up our z-score. Whoops. We're ready to take a look at our z-score, which would be that 2.33 right there. So once again, make sure that you are checking with your drawing to make sure you're in the right column. Make sure that you then take a look at your estimate. Make that rough estimate that you made so that when you find your z-score here of 2.33, we find 2.33, it needs to be a score that's bigger than 2. It is a score that's bigger than 2. So we know that we have found the correct score. We know that we haven't looked up in the wrong column of this particular table. So once we're now confident that we have the right z-score, last thing we need to do is we need to convert that z-score to a raw score. And for that, we visit our familiar formula for recovering a raw score from z-scores. So the formula is the raw score plus the population mean, raw score equals population mean plus the standard deviation multiplied by the z-score that you just looked up. We have all that information. We have a mean of 500, standard deviation of 100. We just looked up a z-score of 2.33. We plug that all in, and we end up with a raw score of 733. So, if you wanted to score in the top 1% on a section of the SATs, you would need to get a raw score of 733. That's how high you need to go in order to get into that top 1%. All right, any questions about that second flip side of it, starting with the percentage and getting a raw score? All good? All right. So you're now ready to do homework assignment number 7. That's chapter 4, part 2. So we did the part 1 of chapter 4, which is some basic probabilities. Now you're ready to do part 2, which will ask you to start with a raw score, get a percent, start a percent, get a raw score. You are good to go on that. And as always, just a reminder, if you're not getting 100% on your pretest, be sure to pick up those percentages in your MyStatLab study plans. Go after those mastery points, and I will update your grades in Canvas so that you can max out your points on those pretests. All right, samples and populations. So samples and populations is basically one of the central ideas in statistics. And the idea is that we only ever have access to a sample. You will never be able to measure an entire population unless your population is extremely, extremely small. So if you are dealing with a population of psychology professors with the last name Yurichevich, it would be a very, very small population. But if you're dealing with any real population, any sort of population that psychologists try to study, you never have access to a population. You only have access to a sample. So we are going to use those samples to say something about populations because we want to be able to say something about everybody, to say something about people in general, so that we can help people in general. So samples in psychology and statistics, they're used to estimate population parameters. You want to know how tall the average individual is? You take a sample of people, you measure their height. You want to know how depressed a population is? You take a sample of individuals, you measure their depression. You use a sample to estimate something about the population. So typically, most often, what we do is we take a sample mean and we use that to predict a population mean. So we take measure a sample, something that we can actually know, and we use that to predict what is the mean of the population. However, this is not as straightforward as it might seem. And the reason is because we usually do not know anything about the population. We don't know what the mean of the population is. We don't know what the standard deviation of the population is. And this is especially true when we're dealing with new populations that might have just emerged. So a lot of times we have absolutely no idea what the parameters are for a population that we're interested in. So for example, a new population that just popped up in the last 20 years are people on social media. Prior to Facebook, prior to MySpace, there was no social media. There was no population of people on social media. So if you are interested in the effects of social media on people, if you're interested in that population, we know very little about it because it's so new, it basically didn't exist. So what do? Well, we start taking a sample from that population. We can't measure everybody, but we say to ourselves, all right, we'll take a sample. We'll take that person right there, and we'll measure where they are. You know, what's their score? We'll take this individual here. We'll take this individual here. This person over here from this population distribution. This person over here from this population distribution. We take a sample of 5 individuals, for example, and then we calculate a sample distribution. So this is a sample distribution, and this sample distribution has a mean that we can measure. We just take the scores from those 5 people, we divide by 5, we add them up, we divide by 5, we find the sample mean. It has a sample standard deviation that we know, because we can figure that out. We'll pop it in Excel, equals STDEV, find their sample standard deviation. So that we know, and in this case, notice that this sample mean is a good estimate for the population mean. In this case, we chose a sample, and it just happened to have the same sample mean as the population mean. So if we were estimating the population mean, this unknown population, using this sample, we came very close to estimating this unknown population mean. So far, so good? All right. However, this doesn't always happen. Sometimes we end up with people from extreme portions of the distribution. So if we're just randomly selecting people out of this population, we might end up with that individual right over there. We might also end up with this individual in our sample, and then randomly select this individual from our sample, and this individual here, and this individual here. And notice that they all have low scores, right? They all have scores that are lower than the population mean. So when we take those individuals and create our sample distribution and calculate out our sample mean, we have vastly underestimated what the actual population mean is. But we don't know this. We have no idea that we did this because we have no knowledge of that population, so we don't know where these 5 people came from. You can't take a person out of a population and identify where they are in that population unless you know stuff about the population. So these 5 people, for all we know, could have come from anywhere in the population, and when we calculate their mean, we have vastly underestimated what that population mean actually is. And to make matters even worse, it can happen on the flip side as well. So we might take a random selection of individuals and end up with that individual in our sample, and that individual there, and that extremely high scoring individual, there's another one there. And maybe we end up with these 5 people in our sample. And in this case, we again can calculate the sample mean, try to estimate the population mean, but this time our sample mean is vastly overestimated the population mean. So this is the sort of challenge that we face when we're trying to estimate a population mean. We don't know where our sample came from. So we have no idea whether our sample kind of had people from the center of the distribution so that it's an accurate estimate of the population mean, or did it have people from the extremes of the distribution so it might be overestimating or underestimating our population mean. So that's a challenge. We have different samples from the same population. They will all have different sample means. So if you take a sample from a population and calculate its mean, and your research partner takes another sample from that population and calculates its mean, chances are those 2 sample means will be different. So what's the real population mean? So most of the time, in fact, your mean of your sample will not equal your population mean. Right? You have to get very lucky in order for your mean, for your sample to equal your population mean. And this is what's called sampling error. And this is the amount of error between your sample statistic and your population parameter. So sampling error, we're getting closer and closer to election times. Anytime that you hear a poll about how candidates are doing in a particular election, they'll always mention the amount of error in their poll. They'll always say, well, you know, so-and-so has 40% support plus or minus 3%. That's an indication of sampling error. They're basically telling you, we don't know, how much of a difference between the actual support our sample has. So that's sampling error. Importantly, though, most of your sample means will not equal your population mean. So the way that we get around this, or the way that we solve this challenge, is we realize that different sample means have different probabilities. So different sample means will occur with different probabilities. They'll occur with more or less likelihood. So for example, let's say that we were entering let's say that you were entering the IQ Olympics. Let's say that there was a competition, a once every 4-year competition, where people are randomly selected from the population and put on a team and they compete in the IQ Olympics. And you and your friend have been randomly selected from the population to compete in the IQ Olympics. And you are being told who your team is, and your team is revealed to be these individuals over here. So this woman is on your team, this man is on your team, this woman is on your team, that woman, that male as well. And you find out that she has a college degree, he graduated high school, she is working on her master's, he has a PhD, and she is currently in university pursuing her bachelor's degree. So you kind of have some from the high end, some from the lower end. You kind of have people from basically, the middle part of this population. When this team is revealed to you, you would not be that surprised. You would not sit there and go, oh my gosh, what are the odds that I would be giving people, this sort of ordinary? What are the odds that I would be giving people that are from, mostly the center of the distribution? You wouldn't be shocked, because that's kind of what you would expect. It seems highly probable that your team would be made up of individuals like this. All right, so that's your team. What about your friend's team, right? So your friend also got invited to the Olympics, and after they reveal your team and after they reveal your friend's team, let's say that you two were talking, and you asked your friend and you said, who's on your team? Like, who did you get on your team? Who was randomly selected from the population? And your friend says, well, the first person that they randomly selected for me for these IQ Olympics was Bill Gates. Oh my gosh, believe it or not, I got Bill Gates. And you'd be sitting there going, wow, that's lucky. That seems highly unlikely. You got really lucky that you got Bill Gates on your team. What about your next player, right? Who are they? Probably somebody, average. And your friend goes, no, my next person on my team, believe it or not, Neil deGrasse Tyson. And you'd be like, whoa, wait a second. Like, that is amazing. That is so unlikely to get one person with a super high IQ, and then you get another person with a super high IQ. What are the odds? And if they say, well, wait, because my next player was Bill Nye the Science Guy, you would be like, oh my gosh, that is bordering on completely unbelievable. And they say, wait, but there's more. I also got Marilyn Vos Savant, the person with the highest recorded IQ in the history of the world. And at that point, you'd be like, this sounds like, it's too unlikely. This is extremely unlikely. And they might say to you, well, it gets even better, because I also got Ruth Lawrence. And Ruth Lawrence is a mathematician, and there she is graduating from Oxford at the age of 13. So, those 5 individuals are on your friend's team. Your friend got this team over here. And notice that when I was reading out those names, it seemed highly improbable. It seemed highly unbelievable. It seemed like that had no chance of happening. And in reality, it does have a chance, right? Bill Gates is part of the population. Neil deGrasse Tyson is part of the population. Marilyn Vos Savant, part of the population. They could be randomly picked. But we all kind of recognize that that team, that sample, has a very low probability of actually occurring. Your team, made up of normal individuals, normal-leveled individuals, that has a much higher probability of occurring. So we're going to use those probabilities of occurring to help us out in our relation between samples and populations. So that's a challenge. How can we tell what the probability is of selecting a sample with a specific characteristics, with specific means from a population before we know anything about the population? So how can we determine what's the probability of selecting a sample from a population? So what is the probability of getting a particular sample? What's the probability of getting a sample with a particular mean? And I keep saying probability, and hopefully that has jogged your memory that for a statistician, probability equals proportions, proportions equals proportions of a distribution. So we can answer the question of how likely is it to get a particular sample by taking a look at a proportion of a distribution. All right, so we're looking for a proportion of a distribution. And this move right here that we're about to do, this is one of the moves where you need to make sure that you are focused in on this right now, because we're going to start going into levels within levels. This is kind of like the movie Inception, where we're going into a dream within a dream within a dream, because we're going to make a distribution now made up of other distributions, right? So we used to have distributions made up of individuals. We are now taking a distribution and we're going to make a new kind of mega distribution out of a whole bunch of distributions. And what do we call that? We call it the distribution of sample means. So the distribution of sample means, this is a collection of sample means, a collection of distributions for every single possible random sample of a particular size that you can get from a population. So it is a distribution of every single possible sample mean that you can get from a population. So for example, in our IQ Olympics example, we could measure the mean IQ of our samples, right? So we have our sample, and we have the mean IQ for each sample. So we take our first sample of 5 individuals, give them IQ tests, measure their mean IQ, maybe their mean IQ ends up to be 110. Whoops. Sample number 1, mean IQ is 110. We then throw them back into the population and we take out another sample of 5 individuals. Sample number 2. Let's say that this is our Bill Gates, Bill Nye, Marilyn von Savant sample, and we measure their mean IQ, and it's like 165, right? Throw them back into the population. Take out another sample of 5 individuals, measure their IQ. Maybe this one will have a sample mean of 90. Throw them back into the population. Take another sample, measure their IQ. Maybe they'll have an IQ of 108. Throw them back. Take another sample, throw them back. Take another sample, throw them back. Take another sample. Do this until you have taken, and this is kind of hard to wrap your mind around, do this until you have taken every single 5-person sample that you can from this population of the world. So at some point, we're going to be on sample 100,585,487,613, and we're still not going to be done, but we've taken this sample here, and we measure their IQ, and they get an IQ of 92. Once we have done this for every single possible sample, we'll have a frequency distribution, right? This is raw scores that can be taken. So these raw scores here can then be taken into a frequency distribution, and every single point in this frequency distribution is a sample mean. Every single one of those scores in this frequency distribution is a sample mean. So this is what I mean by we have distributions that are made up of other distributions. This is your distributions of sample means. All right, so that's what we're going to be dealing with. So that is kind of the intro to that. Let's take a look at it, and we'll back up a little bit. We'll simplify it a little bit. You got the general idea. Let's start putting some actual numbers to this. And once again, we're going to go back to that great tool for statisticians, namely the dice. So if you were to take a look at the population of fair 6-sided dice, right? If you were to take a look at every single dice roll that has ever been rolled by mankind with a 6-sided dice, you would find that the population of dice rolls has a mean of 3.5. Right? So we can prove this mathematically. We can simply add up the numbers on a dice. You got 1, 2, 3, 4, 5, and 6. You add those all up. You get, what would be, 7, you get 21. You divide that by 6, you get 3.5. Right? So the mean score for every single dice roll since the history of time began would be 3.5. If you took a look at the outcomes, you would notice that 1s occurred with the same frequency as a roll of 2, 2 occurred with the same frequency as a roll of 3, 3 occurred with the same frequency as a roll of 4, 4 occurred same frequency as 5 and 6. That's the definition of a fair dice. So this is the population distribution of all the fair dice rolls ever done in the history of humanity. All right, so what do we do if we're taking a look at this population? Well, we can do a sample, and we can take a sample for a single dice roll, right? One dice roll. So we roll a single dice, and then we take its score, and we find the average of the score. So the average of a single dice roll will just be whatever the dice is showing. So let's get rid of this IQ part over here. And we take a sample of dice rolls. So we roll a single dice. If it shows up 5, we sum the scores. It's 5. We divide by the number of scores. That's 1. We end up with a mean of 5. We roll it again. We get a 3. Sum it up. 3 plus itself, 3 plus nothing else is 3. Divide by 1. We get a 3. If we do this over and over and over again, we will get every single possible mean, every single possible sample, and there's only 6 of them, from this, and then we can take the mean of these sample means, and that's what we would find. We would find that the mean of the sample means is going to be equal to 3.5. So that is the mean of a single dice roll, and if you take the distribution of sample means and put it into a graph, in this case and only this case, it will look exactly like your population distribution. So that's the population distribution. That's the distribution of sample means. When you have a sample size of 1, that is the only time your population distribution will look like your distribution of sample means. All right, so bear that in mind. That's the only time that this ever occurs. So let's take a look at what happens normally when we take samples larger than 1. So let's take a look at a sample for 2 dice rolls. So in this case, we have 2 dice. So we roll the dice, add up the score, divide by 2. So if we get a 5 and a 5, that would be a mean of 5. If we get a 1 and a 5, that totals to 6. Divide that by 2, that gives us 3. If we get a 2 and a 3, that would be a mean of 2.5. If we get a 1 and a 1, that would give us a mean of 1. If we get a 5 plus a 4, that would give us a mean of 4.5, and so on and so forth until we have every single possible sample that we can get from rolling 2 dice. There's 36 possible samples that we can get from rolling 2 dice. If we take all of them and we put them into a frequency distribution, first thing we're going to notice is that the mean is 3.5. So notice that the average sample mean has not changed. And notice again that the sample mean is the same as your population mean. So that's one of the reasons why we're doing this distribution of sample means. But importantly, now your distribution of sample means is going to look different. Now it's going to look like this. So this distribution of sample means, not a lot of ways that you can get an average of 1. You got to roll snake eyes. Not a lot of ways that you can get an average of 6. You got to roll double 6s. But 6 ways you can get an average of 3.5. You can roll 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. So you notice that the distribution of sample means no longer looks like the original population distribution. So let's keep the analysis going. What happens when we start doing 3 dice rolls? Right, so now we got 3 dice rolls. So again, roll 3 dice, and they're treated just like subjects that you're measuring. So you roll 3 dice, you take their scores, you find the average for your sample of 3 by summing those scores and dividing by 3. Do that for every single possible dice roll that you can, and you will find out that the mean of all of your sample means is going to be 3.5, so that has not changed. But your sample distribution, your distribution of sample means, has changed. It now looks like that. And we'll continue this. We got 4 dice. Once again, we're looking at every single possible sample that we can get from the population of 4 dice. Add them up, take their averages. We'll find out that the average sample mean for 4 dice is still 3.5. But now your distribution of sample means changes once again. Now it looks like that. And notice that your distribution of sample means is starting to look like a very, very familiar shape. Let's go to 5 dice and finish this off. So we got 5 dice, a sample size of 5. Roll them, take their mean, do that for every single possible sample mean. That will give you a whole bunch of sample mean scores. You take the average of those, the average will be 3.5, same as the population average. You take the sample distribution of sampling means, and that's what it's going to look like. And you can see that it's getting very, very close to that normal curve. So this distribution of sample means is also known as a sampling distribution. This is the important distribution that we're looking at. This is your distribution. It's there in the title. This is your distribution of sample means. Every single score in your distribution comes from a sample, comes from another distribution. It's a distribution of distributions. But importantly, we usually only have one sample. So you might be sitting there and thinking to yourself, well, this is great that we can figure out this distribution by taking every single possible sample in the world, but we never do that as psychologists. We never say, oh, I'm going to test these 14 autistic students, and then as soon as I'm done, I'm going to put them back into the population, take 14 new autistic students. And as soon as they're done, put them back in the population, take 14 new autistic students. And I'm going to do this billions of times so that I can get my distribution of sample means. We can't do that. Usually we only have access to one sample. So what can we do? How can we figure out our distribution of sample means when we're only dealing with one sample? Well, this is where a little bit of mathemagic comes in, known as the central limit theorem. So the central limit theorem is a theoretical theorem that bridges samples and populations. It's what allows us to do inferential statistics. It's what allows us to do psychology. Without the central limit theorem, we would be very limited in who we can help. So this is what the central limit theorem says. So the central limit theorem says that for any population with a mean of mu and a standard deviation of sigma, that basically means for any population. So for any single population that you can think of, it's going to have a mean and it's going to have a standard deviation. So the first thing to notice is that the central limit theorem opens up any population for study. The distribution of sample means with a certain sample size of n will have a mean of mu, so the same mean as your population, and it's going to have a standard deviation of sigma divided by the square root of the size of your sample. So don't worry about why is it the square root of the size of the sample. Just know that it is. The standard deviation of your distribution of sample means is directly tied to the standard deviation of your population. So those two are directly tied with that relation. The mean of your distribution of sample means equals the mean of your population. And then the last thing here is the really big one. That distribution of sample means will approach a normal distribution as the size of your sample approaches infinity. And in reality, it will approach a normal distribution at very low sample sizes, like 20 or 30 is what your book has as a sort of limiting case. So once again, for any population, right, anything you want to study, anybody you want to study, they're going to have a mean of mu, they're going to have a standard deviation of sigma. You can figure out their distribution of sample means. What the mean of that distribution is going to be the same as the population mean. What the standard deviation of that distribution is, it's going to be tied directly to the standard deviation of the population. And the shape of your distribution of sample means will approach a normal curve as the size of your sample increases. And this is why the normal curve is so incredibly important. This is why we spent that time on how to use the normal curve, how to figure out what scores do you need to be in the top 10%. And the reason is that just about every single study that is done in psychology just about every single population that is studied in psychology is going to have a distribution of sample means that is normal in shape. So let's take a look visually once more. So if we have a population distribution that looks like this, which is dice rolls, right? So this was the dice roll population distribution. We don't know what this shape is, right? So let's say that this shape was unknown to us, right? Which is typically what happens in psychology. We don't know what the shape of the population distribution is. It's unknown to us. We can't study something when it's unknown. We have no in to determine how to even begin analyzing a distribution if it's unknown. But look at what happens to the distribution of sample means. When we take a sample size of 1, nothing happens because our distribution of sample means looks exactly like our population distribution. That only happens with a sample size of 1. That's why most psychology experiments don't rely on a sample of 1. It's very rare. They're called case studies. They're usually not done because you don't know anything about the population. But once you go to a sample size of 2, look what happens. We might not know what this population distribution looks like, but we know that our distribution of sample means is going to take on a very particular shape. Sample size of 2, sample size of 3, sample size of 4. For something as small as a sample size of 5, we are already dealing with a normal distribution. And that means that all the tools that we've been working on so far can be applied to this study with a sample size of 5. What if your population looked like that? What if it was a weird dice that didn't have a side with a 1 on it? It had 2 sides with a 5 on it. What about that population? Well, you take a sample size of 1, your distribution of sample means is going to look exactly like your population. Not useful. But notice what happens when you take a sample size of 2, sample size of 3, sample size of 4, sample size of 5. Even with just 5 individuals, 5 people in your sample, your distribution of sample means is starting to look like a normal curve once again. And this will happen for any population. You could have a weird population like this, weird population distribution. Take your distribution of sample means for a sample size of 1. Doesn't really do much, right? Because it looks exactly like the population. Sample size of 2, 3, 4, 5. And even with this weird population here, and even for a small sample size of only 5, we are already getting close to a normal distribution, which means that we are already opening up our ability to study this population. So once again, the central limit theorem says that for any population, does not matter what the shape of the distribution is, doesn't matter what the mean is, what the standard deviation is, any population is going to have a mean and a standard deviation. That population is going to have a distribution of sample means for a certain size sample with a mean the same as the population, standard deviation related to the population, standard deviation divided by the square root of the size of your sample, and importantly, it will approach a normal distribution as n, as the size of your sample, approaches infinity. And just to kind of drive home the point about how important this is about psychology, we know very few populations, right? We have data on very few populations. We know height data for the population. We know weight for the population. We know IQ scores for the population. SAT scores for the population. What we don't know is most other populations. So if you wanted to take a look and study the rates of alcoholism in single fathers who are raising their children alone, if you wanted to look at that particular population, without the central limit theorem, it would be out of bounds. You would not be able to study it. You could not, as a psychologist, even approach studying this population. With the central limit theorem, we might not know what the distribution of alcoholism is among single fathers raising their children on their own. We might not know what that is, but the distribution of sample means from this population is normal. it's normally distributed, which means that we can study this particular population. Let's talk about a new population that didn't exist very long ago. Gay wedded couples. If you wanted to study homosexual couples that got married, to see what are their levels of fulfillment, what are their levels, what are their parenting skills, what are their levels of income. This population did not exist, not that long ago. And without the central limit theorem, if you wanted to investigate this population here, without the central limit theorem, it's off bounds. You can't do it, you can't approach it. Because we don't know what their distribution looks like. We don't know what the distribution of this population is. But central limit theorem tells us that we might not know what the distribution of the population is, but as soon as we start taking samples, as soon as we study 20 gay married couples, 30 gay married couples, we know that the distribution of sample means is normally distributed. And that opens the door to be able to study this population. And really, I mean, the interests in psychology go to so many populations that without the central limit theorem, again, we wouldn't be able to do psychology. So I'll give you one last example. This one was actually done for an advanced lab. So there is a new population, I believe they're called urban bohemians. And they literally did not exist prior to a decade ago. So one of my students was interested in the color perception of these individuals. Do colors mean different things for these particular individuals because they were raised, on technology and they're early adopters? And I had no idea that this population even existed. So if you want to know more about it, there is actually a Wikipedia page on Clarita's Prism. This is a classification system for different demographics, oftentimes used for advertising. And where are they? We are looking at connected bohemians. That was the term. These mix of young singles, couples, and families ranging from students to professionals all have one thing in common: being tech savvy. They are always early adopters of the latest and the greatest thing. I know nothing about this population. I don't know what the distribution of color perception is in this population. I don't know what the distribution of color meanings are in this population. But I do know one thing. You take a sample from that population, and the distribution of sample means is normally distributed. So that opened up the door to be able to study these individuals, even though we know nothing about what their population looks like. So this is what we're going to be working on. This is going to open the door for hypothesis testing. And do remember that we're dealing with multiple distributions now. So we have, for any population with a mean of mu and a standard deviation of sigma, your distribution of sample means will have the same mean. It'll have a standard deviation that is the population standard deviation divided by the square root of the size of your sample. And importantly, it will approach a normal distribution as the size of your sample increases. And this central limit theorem allows us to figure out your distribution of sample means. It allows us to use those Z-scores and that unit normal distribution table. It allows us to apply our tools and open up any population to psychological study. All right, so we're going to take a break in just a moment. Just one last thing I wanted to point out. We are dealing now with 3 separate distributions. And from here on out, make sure that whenever you hear the word distribution, you think very carefully and get very clearly about which distribution are we dealing with. Because we have a population distribution. This is a distribution of individuals. This is the distribution that you're interested in, the population of all individuals. From that population, we can take samples. Samples have their own distributions, right? You take a sample of 20, you can make a frequency distribution of their scores. You take a sample of 30, you can make a frequency distribution of their scores. So samples have their own distributions. And if you take the mean of all the samples of a certain size, you can then put those into a distribution of sample means, right? So we have 3 different distributions. So whenever you come across the word distribution, until you get very familiar with it, take a moment and say to yourself, all right, which one is this? Is this the distribution of population distribution, distribution of individuals? Are these the samples that we took, a distribution of individuals, but ones that we can measure? Or is it a distribution of distributions? This distribution of sample means, which one is it? Take a moment and make sure that you got that straight. All right, so that was the first hour there. So what we're going to do now, let's take a 15-minute break. We'll resume class at 10:15. And just kind of let this sink in, let yourself get acclimated to the idea. And you also got your homework if you want to start on that. And we will start up class again in 15 minutes.